So, hi everyone. I'm Michael Gleischer from the University of Wisconsin-Madison. I'm one of the full papers chairs, and I am session chair for this morning's keynote. It is my great pleasure to introduce Professor Juliana Frady. Juliana is Professor of Computer Science and Engineering in the Tandon School of Engineering at New York University. At NYU, she is part of the Center for Center for Data Science and the Center for Urban Science and Progress. Juliana earned her PhD from Stony Brook and worked at Bell Labs before moving to academia. She was faculty at the Oregon Graduate Institute and the University of Utah before moving to New York University. Juliana is an ACM Fellow and has won numerous other awards. She is chair of ACM SIGMOD, main organization for the data management research community. Juliana comes from the data management community, where she works on many aspects of developing systems that enable people to work with big data. She's particularly well known for her work in scientific data management, especially for helping people keep track of information provenance. She's done important work on the tools for enabling reproducibility in science, in data integration, in large-scale data mining, in the analysis of spatial data, and many, many other things. An important part to this work is that while she works on a wide range of problems, she always looks at how to address real problems in working with large and diverse data. Um, while Juliana doesn't usually work directly on visualization, her broad experience in the issues of working with data should be useful for all of us. And she spends enough time with visualization researchers that she should know how to talk to us. So I'm excited to hear her talk towards usability, transparency, and trust for data-intensive computations. Um, if you have questions during the talk, please send them to me via either the YouTube chat or the Discord channel. There's a Discord channel for this session, and I will ask them to her after the end of the talk. So, Juliana, please.
Mike, thanks a lot for the kind introduction. I also thank the organizers for inviting me. It's an honor to be talking to the visualization community. As Mike has mentioned, I'm not really a visualization researcher, but I deeply enjoy working with visualization people because that has been a great source of problems, as you're going to see in my talk. And also, my papers look much nicer than the database papers. All right, so we're talking about some different projects that I've done that attempt to move, to make progress towards making computations and data-driven exploration more usable, transparent, and to build trust in the results that you obtain from these kinds of explorations. So what we've seen is that data-driven exploration has impacted our society in many different ways. In science, it has led to great advances and discoveries, and it has also transformed how science is done. In addition to hypothesis-driven research, scientists now engage in data-driven hypothesis generation, what Jim Gray and colleagues have termed as the fourth paradigm. We've also seen that companies are capitalizing on data, and it goes without saying that for many businesses, the main source of income comes from the data that they collect. And last but not least, the governments are increasingly collecting data, troves of data, and we hope using them to improve their operations, making policies and informed decisions. Right? And this revolution that we're witnessing has been enabled, has been fueled by the fact that not only are data abundant, but now computing and storage are essentially free. And the challenge that we face now is that mostly the bottlenecks to obtaining insights from this, data and computing lies with people. So let's look at a concrete example of both the opportunities and challenges of data-driven exploration. Let's consider urban data, which is an area that I've been working on for the past several years. Cities are the center of economic activity, and we are witnessing an explosion in urbanization. Half of the world population already lives in cities, and this number is slated to grow to 70% by 2050. And what we've seen is that this fast growth leads to challenges around transportation, resource consumption, housing affordability, inadequate or aging infrastructure, and health crises like the pandemic we're living in right now. The good news is that there's lots of data that are being collected about urban environments and that are being made freely available at open portals. And this data are being collected about different components of these urban environments, infrastructure, environment, and people. And the question is, can we leverage this data exhaust to crack the code of cities? Can we use these data to better understand how the different components, urban components, interact over space and time, and use this knowledge to make cities more efficient, sustainable, and improve the lives of their residents? And the answer is yes. And we've seen a number of examples of this already where urban data has been put to good use. So here are three examples. The first one is a project that came out of the University of Washington, where the researchers built a phone app, an iPhone app, that used both historical and real-time bus data to provide bus arrival predictions. And that has led to a great increase in public satisfactions with public transit. Second example is from New York City, where we are faced with serious problems with illegal conversions as they create unsafe living conditions. If you don't know what an illegal conversion is, it's actually when you alter an existing building to create additional housing units without first obtaining the proper permits or approval from the New York City Department of Buildings. And the problem that we have is, New York City real estate is extremely expensive, so people do this all the time. And the city receives over 25,000 illegal conversion complaints a year, but they only have 200 inspectors. So under Mayor Bloomberg, a team of data scientists got together, led by Mike Flowers, and they integrated data from 19 different agencies. And they looked for indicators that reflect issues in buildings like rat infestation, late mortgage, ambulance visits, and so on. And they crossed that with data from the fire department and built a regression model that tried to predict the buildings that are more likely to have unsafe conditions. And as a result, using this model, they were able to increase the hit rate for inspections from 13 to 70%. Right? And the last example that I have here is on the side of policy. And it's a work done by our colleagues here at the NYU Furman Center for Real Estate and Policy, where they've been doing data-driven policy for many, many decades. And the example that I have here is a study that they did where they shown using data that neighborhoods with concentrated foreclosures see an uptick in crime for each foreclosure notice. And because of this study, NYPD actually updated its policing strategies. So what I like about these examples is that they illustrate the fact that you can use urban data to directly benefit residents, to make cities more efficient, as well as to impact policy, right? And these are great examples. The problem here is that most of these efforts are one-off and require substantial resources because exploring and extracting sites from urban data is very difficult. Right. So the question is, why don't we have many more success stories, given that we have so much data out there available? And there are many challenges, right? So the first one is the fact that we have data. We have lots of data. They come from many different sources. They have different levels of reliability. And because you have so much data spread in so many repositories, even when a data set is available that can answer your question, you may not be able to find it. Another important challenge is the fact that the data are out there, but for domain experts that do not have training in computer science, it's difficult to explore these data. And often they must depend on computer scientists or data scientists to help them with the analysis. And this process greatly distanced them from the experts, from the data that they actually know, and greatly impairs their ability to engage in exploratory research. So they end up doing mostly confirmatory analysis that simply test hypotheses that they already have, and makes it hard for them to actually come up with new hypotheses. And this problem is compounded by the fact that those exploratory analyses are inherently iterative, right? You start with data, you do some computation, you see some plots, you get some results, try to understand them, not quite what you want, then you do different visualizations, use different machine learning, and you keep doing this over and over again as you test and formulate new hypotheses, right? And this involves several try and error steps. And the problem here is that after many steps, it's really easy to get your result and not remember how that particular result was derived. There are many opportunities for you to make mistakes, for the data to have problems. And in the end, in this tortuous path from data to knowledge and eventually to important decisions, many things can go wrong. And the problem here is that bad conclusions, incorrect conclusions, can lead to bad decisions that can have serious consequences. Right? So over the past many years, the long-term goal of my research has been to empower a wide range of users to explore and obtain actionable and trustworthy insights from data. Right? So, the end goal is to how can we reduce the bottlenecks that are faced by humans and make them more effective. And our work addresses problems at the different stages of the data life cycle. We've contributed both foundational methods and systems for data science and engineering. And I'm very fortunate to be part of the Visualization, Imaging, and Data Analysis Center, which is a highly interdisciplinary center that has many researchers that have a passion for data and for solving real problems. And today, what I'll be talking about is a set of projects where we tackled some of these challenges in data explorations, notably to attain usability and interactivity, to guide users in data discovery in exploration, and helping data enthusiasts to build trust in their data and their results. So let's start with usability and performance. And let me start by showing you this system called Urbane that was developed in my group in collaboration with architects from KPF and urban planners that allows the explorations of multiple data layers, multiple layers of urban data. So let's start playing the video.
Urbane allows users to seamlessly explore the city based on multiple 2D and 3D data layers. For example, noise, crime, and as visualized here, subway access. The data can be explored at different resolutions: the city, neighborhoods, and buildings. The opacity of the 3D buildings can be controlled for better visualization of the data layers. Urbane uses a parallel coordinates chart that allows for easy and intuitive filtering of urban datasets. Here we filter neighborhoods for various attributes such as subway access and noise. The bold blue line represents the average of all Midtown neighborhoods. The bold red line is a user-selected neighborhood, here at the Financial District. Filtering of various attributes allows users to understand the characteristics of Manhattan neighborhoods. For example, the Financial District and Midtown are very similar across most attributes. At the neighborhood scale, the same filtering system is applied to individual buildings. Again, the blue line represents the Manhattan average. Here, we filter individual buildings for attributes such as built area, crime, and noise, identifying sites for potential development. Once specific sites have been identified, Urbane gives users the ability to replace existing buildings with new buildings, testing different tower sizes and program combinations for the maximum zoned floor area. The user can generate speculative buildings on many sites. Here we see a hotel with residential, an all-residential building, and an office with residential. Once buildings are generated, Urbane can compute derived 3D attributes from the data in buildings. This includes the view from buildings to selected landmarks, the impact of buildings on sky exposure at the street level, and the impact of the buildings on the views of the existing context. This analysis can be used to evaluate the trade-offs between the value of a new development and its impact on the character of the neighborhood. This can facilitate the design and development process between architects, developers, and city planners.
Okay. So as you can see, Urbane attains usability by allowing experts to interrogate data and explore the results using a visual interface and without having to write queries or programs or scripts, right? That abstracts away all these complexities through this visual interface that is both easy to use and expressive, allowing users to pose a wide range of queries, like, for example, 3D queries, as you've seen here, view impact queries, as well as sky exposure queries. And they can also explore the data layers using visual 2D queries, like, for example, this heat map or the parallel coordinates. So, I mean, the design, I don't need to explain this to you. The design of this visual interface is something that is, difficult and challenging. But when you are able to come up with the right level of abstractions, you can actually get interfaces like this one that are both very easy to use and expressive. But another challenge that we have to face in visual analytics systems like Urbane is that we need to attain interactivity. And in a recent study, Leon here showed that even a 5 millisecond difference in latency reduces the rate at which users make observations, draw generalizations, and generate hypotheses. So that's critical that whenever you have, these queries behind the visual interface, that they need to have sub-second response time. And this is very challenging for interfaces such as Urbane's because, each interaction with the system leads to a potentially large number of queries to the backend. And in this particular case of Urbane, this is especially challenging because the main query used by the system is what we call a spatial aggregation. Right, so Urbane uses spatial aggregation to summarize different data sets, different urban data sets like taxi, crime, subway access. Right, and these queries are what are used in order to build the heat maps. This is what such a query would look like. You want to count all the points in each neighborhood, all the taxi pickups inside each neighborhood, right? And for the parallel coordinates, we actually, for each vertical line in the parallel coordinate, we have to execute one of these queries. So this can be very expensive because spatial aggregation are notoriously computational. They're notoriously expensive queries to evaluate. Right, and here what I'm showing is a query plan. This is what database people do. They plan queries just to illustrate the complexity and why such a query is so expensive. Right. So here's the query where we're trying that is used to build the heat map, right? And what it must first do is to join the set of taxi trips with the neighborhood polygons, right? And this join is done in 2 steps. The filtering step first approximates the polygon with a minimum bounding rectangle, the MBR, which is shown here in blue. And then there is a refinement step where, a PIP test, a pointing polygon test, is performed for each point returned by the filtering step. Right, and this is done in order to discard the points that are outside the actual polygonal boundaries. And the challenge here when we have urban data is that the different neighborhoods are represented by complex polygons that have many different sides. Therefore, these pointing polygon tasks can be extremely expensive. Right. Not only that, we have billions of points also to do this task on. right? So just the join itself is expensive, and in databases, usually before you can aggregate the results here after the intermediate results of the joins must be materialized, which adds overheads here, right? As a result, this query here, of which we need to perform several inner bane, requires several minutes to execute on a commercial database. So clearly, it's not practical to use existing relational technology in order to serve as the backend for a system like Urbane. So how did we solve this problem? How did we address this challenge? To achieve interactivity for these spatial aggregations, we took a fundamentally different approach. And instead of thinking about tables of points and tables of polygons that have to be joined, we considered spatial aggregation from a geometric point of view, borrowing ideas from computer graphics. Right? And here, a spatial join between a point data set and a polygon data set can be viewed simply as drawing the two different data sets in the same canvas, and then looking at their intersections, right? So this is essentially rasterization. Then by using this framing, we can actually leverage the graphics pipelines of GPUs in order to evaluate these queries. So just to give you an idea, let me show you a quick example of how this works, right? So when you're drawing on the GPU, you do so on a pixelated virtual canvas. And we start by drawing the point data set. We draw the first point that falls into that pixel, and we start counting how many points are there in each pixel. So here we have 1 point. We draw a second point. The third point falls in the same pixel as the first one, so we increment its count, and we keep doing that. After all points are drawn, each pixel is going to contain the aggregate of all the points falling in that pixel, right? And in this example, we're using a simple count as aggregate, but we can use any aggregate that is distributive, that has the distributive property, like sum or average, right? So once we have all these intermediate aggregates, we can draw the polygon. And as we raster it, as we paint the different pixels in the polygon, we keep aggregating the total. So we have 0, we have 2, and we keep doing that, right, until we have covered the whole polygon, right? So as you can see, this raster join is very simple, and it has several advantages when compared to traditional spatial aggregation performed in relational databases. Right? First, it frames the problem of evaluating spatial aggregations as drawing operations that are highly optimized for GPUs. Here we can do the join and the aggregation in a single step, and we avoid the need to materialize the intermediate results returned by joins. And there's no need to do pointing polygon tests. Right. Of course, there's some caveats. As you visualization and computer graphics folks know, rasterization can introduce false positives and false negatives. But we actually proposed a variation of the raster join that you can actually specify the error bounds. On the right here, I'm showing the approximate and the accurate. And for the kinds of applications we're looking at with an error bound for, say, 20 meters for this urban data, you cannot really perceive any difference between the two different images. And we also have, if you really need accurate results, we have a variation of the algorithm that returns accurate results, and it does so by performing the pointing polygon test just for the points that line the boundaries of the polygons. Right. So while the idea behind the raster join is quite simple, I was actually, when I first looked at the performance results, I was very surprised because the performance that it attains is very impressive. So here are some results of running the raster join on a laptop equipped with an NVIDIA GTX 1060. For this experiment, we used the New York City taxi data that contains over 868 million trips. And what we're doing here is we are aggregating these trips over all the neighborhood polygons. There are 260 of these, right? So on the left side, we are showing the speed up, comparing the rest or join here in red with different variations, including baseline aggregation that is done on a multi-CPU. And as you can see, you can get up to 300 times speed up. And just to give you a better idea in terms of running time, to aggregate all the different points, over 800 million points over all the neighborhoods for 5 years of data, it takes just 1.1 seconds. Right? So you can get, by leveraging these GPUs, you can really get the interactive response times for relatively large data. Okay. And what we've seen in our work is that the GPUs have a great promise to actually allow users to explore large data on desktops or laptops that are now equipped or increasingly equipped with GPUs. So another example where we used GPUs was for a different class of queries, spatial temporal selection, and we did that in the context of TaxiViz, which is a tool that we developed to help experts explore origin destination data, taxi trips in New York City. Right. So, for example, here in this plot, the expert is trying to compare the time that it takes to go from Lower Manhattan to the different New York City airports, LaGuardia and JFK. Right. And just like for Urbane, we started by trying to use existing relational databases. In this case, we use Postgres and a commercial database, which I cannot name because of licensing restrictions. And as you can see, this simple query here can take anywhere between 20 and 500 seconds using these databases, right? Which clearly is unacceptable for a visual analytic interface. And in this case, instead of coming up with a new operator, we actually built a spatial temporal index using an out-of-core KD3 that leverages GPUs. And again, we attain huge speed ups, anywhere between 20 and 500 times. And queries that take several minutes in the relational databases, we can do it in under a second. Right? So I think that one message in this work that we have is the fact that when you look at traditional, conventional relational database approaches, they're really very slow to compute these kind of queries on local hardware. And in fact, recently approaches have been proposed that make use of large clusters in order to speed up these spatial queries. But these clusters are not very easily accessible, and if it's hard for domain experts to explore data, having to access these clusters makes it even harder. Right? In contrast, GPUs are widely available on commodity hardware, laptops, and desktops. And as we've shown, these GPU-based solutions can lead to interactive response times even for large data. But that's not all roses. And our experience is also that, developing for GPUs is very hard. The implementations are hardware specific. Things that run on NVIDIA may not run on Intel, right? And oftentimes all these solutions, they are specific to particular queries or query templates. It's hard to reuse them across different queries. Every query that you have to support, you need a new implementation, right? And this has actually greatly hampered, a wider use of GPUs for spatial queries. And the question is, can we actually leverage these GPUs without the need to build custom solutions for each different query? And we did this in recent work where we proposed what we call the GPU-friendly data model and algebra. And again, the idea here is that we're borrowing from work that has been done in the computer graphics community for several years. And when we see spatial data, we actually represent it as geometric objects, essentially an embedding of the geometry onto a plane or canvas. And this has several advantages. One of them is that it provides a uniform representation for points, lines, and polygons. And again, these representation is, is very well suited for GPUs, and that's what GPUs have been designed for. Right? And for the algebra, we designed a small set of composable operators that, when combined, can express a rich set of spatial queries. And these operators were adapted from common computer graphics operations that can be very efficiently executed on GPUs. And another big advantage is that they're all hardware agnostic. Right? What it means is that now you have your spatial queries that you can express in the algebra, and you can use infrastructure similar to what is implemented in relational databases, where you specify your query, in a just like you do like in an SQL query in a declarative way. And behind the curtains, you have the system will parse the query, will optimize the query, and create this query plan that can be executed on different kinds of hardware. So you're able to abstract all the complexity, all the implementations of the different operators to the database engine. So this using this algebra, we have many different benefits. One of them is that you can support these spatial queries efficiently, and also in a way that is interoperable with existing relational databases. So you can have queries that interrogate the spatial and non-spatial aspects of data. You get support for query optimization in the sense that you can express your queries declaratively, and the database will automatically find efficient ways of executing the plans, including by exploring different implementations for individual operators. Right? And last but not least, the fact that you write your query and you don't care about specific implementations for hardware, because that's abstracted away by the query optimizer and the algebra implementation. So what are the takeaways of this work? One is that usability and performance go hand in hand, and you need both in order to support interactive exploration in visual analytic tools. And to do that, we need to combine techniques from visualization, computer graphics, HCI, and data management. Right? And for this, it's really important to be part, like I am, of an interdisciplinary group where we have expertise in all of these different areas. Another big message, I think, from this work is the fact that you don't need big iron or big clusters to analyze big data. If you leverage these new kinds of hardware like GPUs, you can actually do large-scale data analysis on your laptop. And this has, great implications in terms of, democratizing data analysis, in particular spatial data analysis. So the StackCVs tool that we developed, because it's so simple, so easy, it can be deployed on a desktop or on a laptop. It was actually adopted by the New York City Department of Transportation, and we got this very nice message from the Assistant Commissioner that says that the speed at which the tool permits us to work has saved multiple hours of staff time and has dramatically improved the unit's outputs and capabilities. And this is actually essentially what they tell us, is that it essentially changed the way that they actually work and analyze their data. Right? And what we hope is that with this new GPU-aware spatial algebra, we'll be able to broaden the use of GPUs for spatial analytics and further democratize spatial data exploration. Okay, so let's move now to the second part of the talk, which is, how can we better guide users in data discovery and exploration, right? So we talk about the fact that, data and computations are increasingly powering important decisions, right? The problem is that, oftentimes, in particular, when you have data from the wild, open data, there can be many issues, and these data come with different levels of quality and reliability, right? So consider, again, one of my favorite data sets in New York City, which is the taxi trips. There are about, or before the pandemic, there are about 500,000 trips a day and over 800 billion trips in 5 years, right? And this data set has been a gold mine. If you go to Google Scholar and you ask for New York City taxi trips, you get over 12,000 results, right? But before using any data, it's important to take a look at the data. And we often do profiling to look at the data characteristics. And for the data set here, we did some simple profiling where we looked at mean, max, average for the different attributes like trip duration, distance, fare amount, tip amount, right, for the different years. And we found very interesting features, like, for example, very large trip durations, distance, fare amount, and tip amounts in 2010. And even stranger values for the minimum values, where we have negative trip duration, negative trip distance, and fare amount, right? If we plot this data, we also see some additional quality problems. So this is Manhattan, and these are all the taxi pickups and drop-offs. But then you also see lots of taxi pickups and drop-offs in the Hudson River and the East River. And I can guarantee you that there are no amphibian taxis in New York City, right? So there's lots of data quality issues, and we actually written a paper just with data quality problems found in the specific data set. The challenge is that while in some cases it's easy to determine that, a particular feature is an error in the data, in many other cases, the issue is a lot more subtle. So if we look here at this plot where I'm showing the total number of trips, daily trips, taxi trips for 2 years, 2011 and 2012, you can see that, for both years, you have similar patterns, right? Except that in August 2011 and in October 2012, you have these huge drop in the number of taxi trips. And you can ask yourself, are these big drops data quality issues, or is it the case that they correspond to real events, right? Interestingly enough, if you actually cross these data with weather data, specifically wind speed data, what you can observe is that the big drops in number of trips corresponds to days where you have unusually high wind speeds, right? And essentially these big drops here were actually Hurricane Irene and Hurricane Sandy, right? And given that, so in this case, I live in New York City. I was actually here for Hurricane Irene and Sandy. So this is kind of like cheating, right? But the big question is, given that we have lots of data sets available in many different repositories, can we actually do this in an automated fashion? Can we use data to explain data? Right? And this is the problem that I call relationship discovery. And the idea here is that given a large collection of data sets, can we infer relationships between data sets in the collection? Right? And the goal here is to look for relationships that take both space and time into account, and that also capture atypical behavior, right? So when we have these weird features, big drops in data, can we find corresponding features in other data sets that can explain this atypical behavior, right? So what is hard in this problem? One is scale. You have lots of data sets. If you consider just the New York City open data, there are over 1,900 data sets, and each of these data sets has many attributes. On average 8 attributes per data set, but some data sets have, say, like the weather data have 200 attributes, and some data sets are small, but some are very large. Like, for example, the taxi data set has about 180 million trips per year, right? The other challenge comes from the fact that these data come at different spatial temporal resolutions, and you need to compare data at these different resolutions. And to do so, you end up with a combinatorially large number of relationships to evaluate. Just to, as a point of comparison, for a single spatial temporal resolution, you have to evaluate over 2.4 million possible relationships amongst only 300 data sets in the NYC Open Data. Right? So what did we do? We proposed what we call the data polygamy framework that automatically discovers the spatial temporal relationships between data sets. And we call it data polygamy because each data set can be connected to 0 or more data sets through different attributes, right? And the goal here is to guide users through these relationships in data discovery analysis by allowing them to pose queries such as the following. Given a data set D, find all data sets that are related to D. And with such queries, you can not only identify potential data quality issues, but also explain interesting features in the data. So how does this work? The first thing we did is that we borrowed this concept of topology-based relationships from computational topology. Right? So we start by using a topological representation of the data where each attribute in each data set is represented as a set of time-varying scalar functions. So here's an example of a time-varying scalar function that represents density of taxi trips in New York. Right? And this has several advantages. One of them is that we have now a uniform representation for all different data attributes, right? They all represented by these scalar functions. And another big advantage is the fact that these scalar functions naturally capture atypical behavior, right? Or salient features in the data. And the salient feature is going to be a spatial temporal region whose behavior differs from that of the neighborhood, right? And in the function, these actually correspond to the critical points of the function. And the way that we define this topology-based relationship is that we say that two attributes are related if their salient features overlap in space and time, right? So this is how the framework proceeds. So we start by looking at all data sets in the collection, and we transform each attribute into a set of time-varying scalar functions. Then we identify the features, the critical points for all the different scalar functions at different resolutions. So if data comes hourly, we look at hourly, daily, weekly, and so on. Right, and to do this, we use this merge tree index that is very efficient to construct and also to extract the features. And once we have those, we compute the candidate relationships. Right, so if we have two different scalar functions, we align them, and we find positive relationships if you have two peaks that overlap in space and time, and you can have negative relationships if a peak overlaps with a valley over space and time, right? So this is kind of like an analogy here would be positive and negative correlations, if you will, right? But when we do this, we can find many, many different relationships that can be simply coincidental. So we need to evaluate these relationships and ensure that they're statistically significant. And for this, we developed a restricted Monte Carlo procedure that will test the statistical significance by accounting both for the spatial and temporal proximity. And we use this to prune relationships that are coincidental. And I can't get into the details now, but you can find them in the paper. So does this work, right? Is this really scalable? So we did an experimental evaluation where we first implemented the framework using MapReduce. And what is nice is that all the different operations, feature identification, and also relationship evaluation are independent. So this is a problem that is invariantly parallel and can be easily implemented using MapReduce. And we ran this job in, just to give you an idea, on an old cluster that had 20 nodes. And for computing all the relationships, deriving all the relationships for over 300 data sets from the NYC Open Data, it took a little bit over 200 minutes to compute both the scalar functions and the features. And we've also shown that the approach is efficient. And, if you add more iron, you add more nodes, it will scale linearly with the number of computer nodes. Right? So it works efficiently, it's practical, but then the question is, does it actually find interesting relationships? And we have a number of case studies in our paper, and here I'll talk about one of them that I found particularly interesting, which is, if you have this question, you come to New York City, and it's raining, and you're going to see that it's really hard to find a taxi. Right? Then you may ask, why is it the case that it's so hard to find a taxi when it's raining? If you're using data polygamy, you can attempt to answer this question by posing the following relationship query. Find all relationships between the taxi data set and the weather data set. Right? And not surprisingly, the system actually identifies a negative relationship between the number of taxis and average precipitation, which suggests that when it's raining a lot, there are fewer taxis on the streets. Right? There's also been a long-running hypothesis that the reason that there are few taxis when it rains a lot is the fact that taxi drivers are target earners. And when there is rain, you get more passengers faster, you make your quota, and you go home. Right? And we also find a relationship that supports this hypothesis, where we found a very strong relationship between precipitation and average fare. But what was interesting in this example is that there is a 2014 paper that refused this hypothesis of taxi drivers being target earners. And, the author did not refuted this hypothesis because he could not find a correlation between drivers' earnings and rainfalls. And there are few issues with his analysis. One is that he did not take into account the amount of rainfall. He just considered it as a binary value. It's either raining or not raining. And the other one is that he considered the whole time period, right? The periods with very sparse rain are considered equivalent to those having higher rainfall. Right? So to me, what is interesting here is that it underscores the importance when you're doing data analysis to consider these salient features and relationships that actually involve these salient features. Right? And again, as I said, you can find a number of other examples in our paper from Sigma 2016. So what are the takeaways from this project? I think what was interesting to me is that we can, at scale, use data to explain data and gain trust, either, either determine whether, a particular feature is an error or whether it can actually be explained and it corresponds to a real event. We've also done follow-up work where we consider different kinds of relationships in addition to these topology-based relationships by using different event detection methods, different alignments, so that we can capture events that have lingering effects. And we have a recent paper that is going to appear at the ACM TDS. Right? Word of caution is that approaches like polygamy should be used as for hypothesis generation, right? So essentially it gives you insights, but you need to further validate those in order to ascertain that a relationship really holds, right? And besides its use for explaining features in data, more recently, we've actually been using this idea of relationships to also help with data discovery and augmentation. And the idea here is that can we actually find data that can enrich analysis and improve machine learning models? Right, and this is something that we started to do in the context of this DARPA D3M program. And let me give you an example so that you have an idea what I'm talking about. Right. So let's say you have an MTA analyst that is working on reducing traffic fatalities in New York City, and there's lots of data out there that can help him create a model, like, for example, the number of taxis, collisions. And he starts by creating a simple random forest regressor using this data, and he gets an error that is relatively high, 75.5, right? But he's an expert, and he knows that there are a number of factors that can contribute to collisions and fatalities. Like, for example, the weather. If it's raining or if it's snowing, it's more likely that accidents are going to happen, as well as city bikes. If there are many bikes in the city, they're more likely to be fatalities, right? And fair enough, if he actually augments his original data and looks at weather and city bike, he can substantially reduce the mean error in his regressor. Right. And again, the question here is, can we actually leverage large data collections to automatically recommend these augmentations, right? And data sets that an expert may not have been aware of, right? And this is exactly what we're doing in the context of Octus, which is a data set search engine, very much like Google helps you find documents. Octus helps you find relevant data sets. And the system supports data augmentation queries. Given a data set, you'd like to find all data sets that are related with D in different ways, right? And we support queries like, find data sets that can be joinable and add new features, say, for your machine learning model, data sets that can be union or concatenated that, can give you more samples to improve your model. And we are also working on supporting other augmentation queries like finding data that can be correlated or topologically related in the, like what I've shown with data polygamy, right? So the idea is that, you can give a data set like New York City taxi data, and you can find a number of other data sets that are related or can be joined with that data set. Right. And the system also supports data discovery queries similar to a search engine. You can type keyword queries and you can get data sets that match, but you can also have more advanced queries like spatial temporal queries, where in this case you can select a region and it's going to return all the data sets that fall in that region. Right. Again, I don't have much time to talk about details. I'd be happy to answer questions. And also, if you want more information about Octus, you can go to our website. Oh, sorry, octus.beta-nyu.org. Right. Okay, so for the last part of my talk, and I have 5 minutes for that, I'll talk briefly about reproducibility, responsibility, and trust. Right, and again, going back to the fact that data and computations are increasingly being used to make important decisions. Right, but we all know that the path from data to insights is a very tortuous one, and you have to go through many different steps to get to a particular result, right? And in this case, the user went, got some data, cleaned, analyzed the data, created models, refined models, improved the model, augmented data, got a very good result. And then a few days later, and this is actually a real example, he reran the model, and all of a sudden the F measure was greatly reduced. And he didn't remember anything that he had done in order for that drop to happen, right? So why was there a decrease in F measure, right? And this is a common problem that people face in data science and data engineering, and that was nicely summarized by Kandel and others in a vast 2012 paper, right? An analysis has 30 different steps. It's tempting to just do this, then that, then this. You have no idea in which ways you're wrong and the data are wrong. And when you get your result, it's difficult to figure out, why do you have that particular result. And the challenge here comes from the fact that there are many components that contribute to a given result. There are problems that can occur in the data, in the hyperparameters that you use, in the computational steps, or even in your computation environment. In fact, this problem here, where the model was rerun and the F measure dropped, was actually an upgrade on scikit-learn that led to this reduction, right? So there's a huge need nowadays, in particular, as more and more people, broad range of users are adopting computational tools and engaging data-driven exploration on how we explain results and how do we build trust in these results that we generate. And there are key ingredients in order to answer these questions. The first one is transparency, which you can get by capturing detailed provenance of the steps that you followed. And the other one is the ability to reproduce, rerun, as well as replicate the computational steps that you performed. And as Michael mentioned, this is actually an area that I've done a lot of work in and I'm very passionate about. We addressed some of these challenges in previous work. In particular, we proposed the provenance model that which we call change-based provenance, that essentially captures this provenance of an exploratory process as a series of computational actions captured as a tree that reflects all the trial and error process that one used in order to solve a particular problem. So whatever results you have derived, you can actually go back and see exactly the steps that led to that particular result. And in this work, we've shown a number of benefits of having these provenance of the exploratory process. Not only it enables one to reproduce and replicate the steps, right? But it also has other benefits like the support for reflective reasoning, the ability to explore parameter space, compare results, and very importantly, the ability to reuse knowledge. And we've shown that we can use provenance in order to help users refine computations by analogies, as well as recommend next steps, like as illustrated here. You read the data set, and by looking at provenance at what other people have done, you can actually recommend full pipelines that can, in this case, derive different kinds of visualizations. Right, and there's been a lot of work on provenance systems that enable provenance capture that gives you all these benefits. Right. But one more recent piece of work that we've been doing is on trying to use provenance to build trust, and in particular to help debug data science pipelines. Right? So here what I have is an example of a machine learning pipeline template, something that is used, say, in AutoML systems to try different kinds of estimators and try to come up with, the best configuration for a given problem. I read the data set, I split, train, and test. I run an estimator, and I compute the score, right? And I run this with different parameters to try and find the best configuration. And I noticed that some of the configurations lead to failure, meaning that they have a very low, say, F score when you use gradient boosting, right? And you can actually ask, why do these specific configurations fail? Right? By looking at the provenance of this log of execution, you can actually identify common features in these failing configurations that can give you a hint in terms of what might be causing that. In this case, we have two attributes. Library version, the scikit-learn library version is 2.0, and the estimator is gradient boosting. When you have these two values, you always have failure. But this may not tell the whole story, because there can be other factors or other values that are actually contributing to the failure, right? And in general, you need to run additional configurations in order to either find additional causes or to confirm that indeed what your hypothesis here is actually true, right? The challenge here is that it's really not feasible to try all different combinations of values for these configurations, because executing pipelines is expensive, right? So you need to have methods and algorithms that carefully select the configurations that will be run to avoid non-informative executions, right? And this is algorithmically similar to approaches that do parameter tuning, except that when you have these algorithms, they actually focus on finding good configurations, while our goal here is to try and explain the configurations or what causes problems in these configurations, right? And we've recently built the systems and developed a set of algorithms to help debug these computational pipelines. And it works as follows. First, it examines the provenance of execution, the log, to identify the candidate causes. And you can view these as your initial hypothesis for the failures. And then it goes on to iteratively execute new configurations, new parameter values to try to prove or disprove these initial hypotheses. And in our paper, we've actually proposed a series of efficient algorithms that are able to identify either one root cause or all minimal root causes for the behavior that was identified. And we've shown that the algorithm is efficient, and it often finds root causes using only a number of pipeline instances that is linear in the number of parameters, right? And this is a good indication that this approach is actually practical. We've evaluated this over a number of different types of pipelines, over a variety of source of errors, including in the context of a collaboration that we have with folks in a major software company. And the results are quite promising. And if you want more information about this, you can both look at the paper or the source code of the system, right? So some of the takeaways, when you're considering trust and provenance, is that when you're doing data exploration, provenance is critical. It has many benefits besides reproducibility. It can help streamline data exploration and build trust. And this ability to actually replicate computational steps is critical in order to help the identification of root causes of problems or weird behavior in computational pipelines. And I think that this is a very important area of research, and I see many opportunities to use similar frameworks to besides finding bugs and explaining bugs and features, to also assess fairness and look for biases in computations, right? And I'd also like to underscore the fact that because visualization has become critical in data science and engineering, we really need to make sure that visualization research is reproducible. We've seen quite a bit of progress in visualization conferences and papers, but a lot more needs to be done. And Jean-Daniel Faquet and I are actually preparing a paper where we discuss these issues in visualization and make some recommendations that will appear soon. So keep an eye on that. And I'd also like to tell you about, if you're interested in reproducibility and replicability in science, I'd like to point to you to a recent report by the National Academies that provides a very comprehensive view of this topic, and as well as of the state of the art and the challenges and opportunities for science and replicability. All right, so to conclude, and I'm sorry I'm a little bit late, I hope I've convinced you that data-driven exploration is important. That has, transformed our society, science, government, and industry, and that there's a lot of work that we need to do and that we can do to empower domain experts to be able to better leverage both data and computation, right? As I've shown, you can actually develop new methods that can guide users as they generate test hypotheses, as well as help assess the quality of and debug their results. And to do so, it's critical to have interdisciplinary teams and collaborations with domain experts, right? And I hope that the work that I've presented today served as an example of how we can actually combine methods from visualization, data management, computer graphics, statistics, right, to build solutions to very real problems in this area. And what is nice is that these interdisciplinary collaborations help build this virtuous cycle where by solving domain problems, we actually find new requirements and for research in computer science and data science, right? And I think that there's a lot of work that we need to do, and we are very well positioned to have a tremendous practical impact as data-driven exploration becomes even more popular and more people use computer and data to derive insights and make decisions. With this, I close. I have to acknowledge all my collaborators, which is a big group, funding agencies, and thank you all.
Okay, I think I'm back on. So Juliana, thank you for the talk. You're getting a round of virtual applause. I'll give the applause of one.
Thank you.
So over the course of the talk, there were a bunch of interesting questions and comments to come up. Maybe I'll sort of work backwards a little bit from some of the last topics of the talk. Of some of the questions that came up. One of the things that you pointed out was as you when you have this combinatorial explosion of potential ways of mixing databases together, there's a great risk of having spurious false connections happen. And you point this out, and even saying that you should only use this for hypothesis generation. So one question is, how do you support this kind of like, well, there's going to be a zillion of these spurious things. How do you support somebody in figuring that out? And then a specific question that somebody asked about this is, do you have an interesting anecdote of a negative case? I mean, you showed us the nice positive example of taxis and rain, but do you also have a spurious negative example that?
So we do look for statistical significance, right? So that's what we use the Monte Carlo procedure for, right? So when we find a relationship between two different data sets, we fix one data set and we randomize the second one in different ways, and we look for the relationships, right? So if we find relationships between the original data set and the randomized one, strong relationships, right, then it's likely that that's a coincidental relationship, right? So here we actually use p-values in order to determine this, right? So we address it this way. But I think that the negative is an example that I have is that there are actually some interesting and correct relationships that are found not to be statistically significant, right? And the example that I showed is one of them, when you have hurricanes and drop in taxi trips, right? Over the past many years, 5 years, there are only 2 hurricanes, right? So you only have 2 instances of this event. So that relationship is actually not statistically significant, but it's correct, right? So I think that this problem in terms of what we show to the user and how you let the user explore these relationships is an interesting one that deserves more research.
So a related question, someone was recounting that at supercomputing, one of the invited speakers talked about how when you have very large data sets, you sometimes get led astray because there is so much extra stuff in there, and that sometimes it's better to start with smaller data sets to sort of get more accurate results because you're not led astray by things like that. Do you have any experiences that that are similar to that?
I mean, so there's lots of, like when you're cleaning data, right? That's easier to get a sense with smaller data set. But for this particular problem that I talked about, when you're really trying to look for interesting features or salient features in data sets, it's okay to look at the large data set because by definition, you're going to have few salient features, right? So in a way, looking at the salient features is a way to look at the smaller subset of the data set. Does that make sense?
That one wasn't my question, but let me connect that to another question, which is more connected to something I was wondering. When you start looking for these specific salient features, which at some point you defined to be like critical points, doesn't this become sensitive to outliers and noise, because an outlier or noise often shows up as a salient feature because it sticks out?
Exactly, right? But that's exactly the point. We are looking for outliers and we're looking for near outliers. And these are the ones that we want to explain away, right? We'd like to figure out whether that's a problem or if that's a feature, right? So we're actually interested in those.
Okay. So another set of questions were sort of from the beginning of the talk when you were talking about the GPU data model. And there were some questions around that about what I'm trying to decode from some of the topography, but the data model, does it also support sort of more standard queries and integrate with standard queries, or is it only for the interactive spatial queries?
No. So the idea is that the algebra is general, right? And it can actually be integrated with a relational backend. So you can have a SQL query that combines spatial components with, the other, SQL, doing selections, projections, and regular joins, right? So that's something that can be handled at the optimizer level.
And I think a question very related to that answer, but right now when we build interactive systems, we typically use tools that things like D3 and WebGL that are not necessarily fitting into a relational data model and the sort of even the model of thinking of the world as queries. How do you see the integration of these sort of the spatial algebra based tools that might give us the ability to get great data performance with the common ways that we build systems, or will we just have to rethink the way that we build systems?
So the question is, how do you do that? Because in order to build your visualizations, you need the data, right? So you need to have an API that brings the data from somewhere in order to build your visualizations, right? So this spatial algebra can be used as that API, right? And this is exactly what. So this is Urbane uses such an API, except that now we have our own backend to support that, right? But maybe you can elaborate on the question, because all the systems that we have built, like Urbane or TaxiViz, they issue these queries in order to get the information to populate the visualizations.
So I guess maybe a way to rephrase that question based on, so when a team that combines database experts and visualization experts are able to put these two tools together, in the future, can we consider ways to better integrate these two ways of working? There's good ways of working with data. There are good abstractions for working with data. There are good abstractions for working with visual design. They usually, the systems that are good at one don't consider the other well. Is that a fundamental issue, or is it just that no one has thought to put good visual abstractions and good data abstractions together in the same sort of?
Oh, I see. So you're talking about a tighter integration. Yeah. So So I think that maybe because I'm a database person, I always think about the screen interface and Cree API, and the systems that we developed have been developed this way, right? Yeah. So I'm not very familiar with D3, so it's hard for me to figure out what would be the right way to access data from D3.
Okay. I'm just sort of looking through here. Here actually, there's another question. There's a question here about the sort of I think asking for sort of a little bit better understanding of how the rasterization and discretization were being exploited for accelerating the spatial aggregation, and then asking that could ray tracing be used to also tackle these kinds of data aggregation and data query problems.
Right. So in terms of rasterization, I think that it's like the example that we shown, right? So essentially, we do the join by drawing on the virtual canvas of the GPU. It's exactly what I showed there, right? We haven't really thought about using ray tracing for that.
Okay. And then some things that one comment that came up, which is to put in a plug for there is a star, and I'm not sure when that is, on the issue of trust in learning and data-centric systems and how visualization might connect to that. So there was a plug for that, and one other sort of open question, which was sort of, I'll try to phrase it more as a question because it was a comment, was at these spatial things, when you get to scale, you kind of got this, rainfall is not just either yes or no. There's interesting patterns and sort of details. So there's unlikely to be sort of the answers to some of these questions might be very complicated. How do you, when you have a question like how do taxis connect to rainfall, where the answer is a very rich and complicated thing? How do you connect those questions to coming up with ways of presenting the richness and complexity of the answers?
Right. So that is that's a very interesting question, right? Because right now, what we've done is we find the relationships, and different kinds of relationships can be topological, can be joins, can be other. As I mentioned, the new technique that we're actually looking for temporal outliers, right? But we really haven't made. We did build a visual analytics tool that we demoed at Sigmod in 2017 that attempted to help users in exploring these relationships, exactly like what you say, right? So looking at, say, relationship strength, looking at the filtering relationships based on attributes in the data, right? But that was, very preliminary work. But I agree that this is an interesting area to explore, because there's the devil's in the details, and there's lots of different, I would say, attributes for relationships that can help the user better understand what the relationship entails and whether they can trust the relationship.
That's great. Good. So this has been very interesting. So I'd like to again thank you for your great talk. I'll
you.
clap, but there's a lot of virtual clapping going on, and I think this might be a good time to stop and give people a chance to have a break before the best paper sessions. So
Great.
again, thank you very much, Juliana.
Thank you so much, Mark. Thanks, everybody. Bye.